strange visitor from the deep galactic dark, 3I Atlas, has slipped into our solar system. It's only the third confirmed interstellar object in history, and NASA's Planetary Defense Network is now locked in to watch its every move. In this video, we'll break down what it is, why scientists are excited, and how planetary defense actually works, without the hype and with the facts. Imagine a snowball that formed around a distant, unfamiliar sun, built from ancient ices and dust before our own planets were even finished growing. Now imagine that snowball being nudged over unimaginable stretches of time out of its original home and set adrift between the stars. That's the story behind 3I Atlas, an interstellar wanderer that just happens to be passing through our neighbourhood for a brief, one-time visit before slipping back into the deep, dark ocean of space. When astronomers call 3I Atlas interstellar, they mean it literally. It does not belong to our solar system. Most comets and asteroids we study were born with the sun, travelling in long, stretched ellipses that loop back again and again. 3I Atlas is different. Its path through space is open-ended, a one-way arc that doesn't close like a racetrack. In plain language, it's moving too quickly and on the wrong kind of curve to be captured by the sun's gravity. That's how scientists know it's a visitor, not a resident. Think of the solar system as a quiet cul-de-sac where the planets are well-behaved neighbours, circling in predictable lanes. Every so often, a car from a far-off city cuts through the street, never to return. 3I Atlas is that out-of-town car. It will swing around the sun once, change direction slightly as gravity tugs on it, and then head back out, forever. There's no "see you next time," there's only now. The name tells you a lot. 3 marks it as the third interstellar object ever confirmed by astronomers, following the famous first visitor Oumuamua and the second, the comet Borisov. I stands for I, the code astronomers use for interstellar, and Atlas honours the survey that spotted it, the telescope scanning the sky each night, designed to catch fast-moving, faint objects before they slip away. In other words, the title is a tiny story, Third Interstellar, found by Atlas. Even the name carries the sense of a traveller shouldering a great distance. What exactly is it? All signs point to a comet, an icy nucleus that sheds gas and dust as it warms in sunlight, growing the fuzzy halo called a coma and, if conditions are right, a tail. That's thrilling because comets are time capsules. The ices that make them up, water, carbon-bearing compounds and other frozen gases, preserve the chemistry of the nursery where they formed. When the sun heats those ices, they turn to vapour, carrying tiny grains with them. Telescopes then study the light reflected and emitted by that material, teasing out chemical fingerprints. No equations needed. It's like reading an ingredient list written in starlight. With 3I Atlas, we're reading a recipe from another kitchen entirely. If its chemistry looks familiar, that suggests planet-forming processes across the galaxy often cook with the same basic ingredients. If it looks unusual, that tells us other solar systems may follow different rules, make different kinds of worlds, or simply evolve along timelines we haven't considered. Either way, every observation sharpens our picture of how common or rare solar systems like ours might be. How do astronomers become confident something is interstellar without pulling out chalkboards and complex math? They watch it night after night and draw a line through the sky from one position to the next. The line isn't actually straight. It curves as gravity nudges the object. For local comets, that curve closes back on itself, forming a loop that will eventually bring the object around again. For 3I Atlas, the curve never closes. That persistent open shape, combined with the way its motion doesn't fit any bound orbit, is the big tell. In more everyday terms, it's not just taking the scenic route, it's on a freeway that never circles back. Another clue lives in its brightness. As 3I Atlas approaches the sun, it wakes up. Ices turn to gas, dust drifts away, and the object brightens. Patterns in that brightening help astronomers estimate how reflective it is, how active its jets are, and roughly how large the core might be. We don't need to pin it down to exact numbers to appreciate the point. 3I Atlas behaves like a comet because it is one, just one that started life under a different star's light. It's natural to ask whether a visitor like this is dangerous. The short answer, no. 3I Atlas is being tracked by a global network of telescopes, professional surveys, space agencies, and dedicated amateurs who are very good at figuring out where objects are going. The path for this traveller keeps it at a vast, safe distance from Earth, the way a plane at cruising altitude passes miles overhead. Noticeable if you're looking for it, but not a threat to anyone on the ground. The real story isn't risk, it's opportunity. And what an opportunity it is. Interstellar objects are astronomy's equivalent of driftwood washed up on shore after a storm. You don't know what distant coastline it came from, but by studying its wood, shells, and seeds, you can guess at the ecosystem that shaped it. 3I Atlas may carry dust grains that formed under different temperatures, or ices mixed in ratios we don't usually see here. Maybe its surface is darker or lighter than expected. Maybe its dust scatters sunlight in a slightly different way. Each little maybe is a data point that either reinforces what we think we know about planet formation, or challenges it in a productive way. There's also a human angle to all this. We've gone from never seeing an interstellar visitor at all to recognising several within a handful of years. That's not because the universe suddenly changed, it's because our tools did. Surveys now patrol the sky with a regularity and sensitivity that would have seemed like science fiction a generation ago. 3I Atlas is a symbol of that progress, a testament to patient, systematic watching. It reminds us that discovery often comes not from a single eureka moment, but from nightly diligence. Look, measure, look again. If you could ride alongside 3I Atlas, the view would be humbling. Behind it, a faint line marking the gravitational handshake with our sun. Ahead, a vast darkness sprinkled with stars it will never meet. Comets from our own family return like migrating birds, revisiting the inner solar system after long, cold seasons. This one is more like a wild goose passing high overhead on a path that traces an entire continent. We get one pass to take our measurements, capture our spectra, and learn what we can before it fades into background starlight. So when you hear astronomers speak with excitement about 3I Atlas, it isn't because they expect fireworks in the sky. Most of us won't see it with our eyes at all. The excitement comes from what it represents, a tangible piece of elsewhere. A messenger that doesn't speak in dramatic visuals but in subtler signals. Reflected light, the whisper of gas becoming vapour, the way dust trails behind like a signature. From those whispers, we reconstruct a story that began under alien suns and now intersects briefly with ours. In short, 3I Atlas is a comet-shaped letter from another star system, delivered by gravity and time. We'll open it carefully, read what it can tell us about how worlds form and change, and then file it in the grand archive of things that pass through our sky once and never again. That's what makes it special. That's why the world's telescopes are paying attention, and that's why, long after it vanishes into the dark, the data it left behind will keep working, quietly reshaping our understanding of the cosmos. When people hear planetary defense, they picture sirens and last-minute heroics. In reality, it's a calm, methodical system built to notice unusual visitors early, measure them precisely, and share facts quickly. That system lights up for anything out of the ordinary, not because danger is expected, but because information is power. An interstellar object like 3I Atlas fits that bill perfectly. It's not from here, it doesn't follow the usual traffic patterns, and it gives the network a rare chance to exercise its full toolkit in public view. The goal isn't drama, it's clarity. Start at the centre, NASA's Planetary Defense Coordination Office, PDCO for short. Think of PDCO as the conductor of a very large orchestra. Its job is to find, track and characterise asteroids and comets that come near Earth. and to coordinate how the scientific community and civil authorities would respond if anything ever posed a real risk. Day to day, that means funding the sky surveys, setting priorities, and making sure that when something interesting pops up, everyone knows who plays which part. The first musicians in that orchestra are the wide-field survey telescopes sweeping the sky every clear night. Systems like Atlas in Hawaii, Chile and South Africa, Pan-STARRS atop Haleakala, Catalina in Arizona, and others continually take images, subtract yesterday from today, and ask, what's moved? That's how fast, faint objects are found in the first place, by relentless repetition. Atlas alone is designed as an early warning net for small, fast movers. It scans the whole sky several times a night. When a visitor like 3i Atlas is noticed, it enters a global relay race of follow-up measurements. All those raw positions flow to the Minor Planet Center, astronomy's official clearinghouse. The MPC checks, posts and updates observations, issues provisional designations, and hosts the confirmation page, where astronomers coordinate rapid follow-up. It's the switchboard that turns a handful of spots on a few images into a tracked object with a preliminary path. From there, the orbit work shifts into high gear at NASA's Center for Near-Earth Object Studies, CNEOS, at JPL. CNEOS runs two crucial engines. One is Sentry, which continuously scans the catalogue to see if any known asteroid or comet could intersect Earth's position in the future. The other is Scout, a rapid response tool that looks at brand new discoveries on the MPC's confirmation page and asks, is there any chance this is an imminent impactor? Most of the time the answer is no, and that's the point. Scout clears false alarms fast and Sentry keeps a sober, constantly updated risk table for the long term. You've seen this machinery in action. In January 2024, a tiny space rock, too small to survive entry, was discovered only hours before it hit the atmosphere over Germany. Scout predicted when and where the fireball would occur, giving scientists a real-world demo of the alert pipeline from first sighting to accurate public notice. That was planetary defense doing exactly what it's meant to do: inform, not inflame. When a newcomer like 3i Atlas appears, planetary defense doesn't just ask, is it dangerous? It asks a whole series of practical questions. How certain are we about the path? What's the range of possible distances from Earth at closest approach? How fast is our uncertainty shrinking as more data arrive? The network then choreographs follow-up to tighten those answers. More optical astrometry from pro and amateur observatories, spectroscopy to see what it's made of, and, when geometry allows, planetary radar. Radar deserves a spotlight. NASA's 70-meter Goldstone dish can ping suitable targets with radio waves and measure their distance and speed with exquisite precision. A handful of minutes on the dish can shrink an orbit's uncertainty by orders of magnitude, turning a blur into a well-pinned track. Even when an object is never a threat, those radar snapshots harden our models and sharpen the whole system's readiness. Over the past year, Goldstone has delivered detailed images and improved orbits for multiple near-Earth asteroids, proof that radar remains one of planetary defense's sharpest tools. There's also the international layer. The International Asteroid Warning Network is a global coalition that shares observations, harmonizes messaging, and acts as an information hub if a genuine hazard ever appears. In parallel, the Space Mission Planning Advisory Group, SMPAG, under the UN umbrella, develops playbooks for what space agencies could actually do, how to organize, what options exist, and how to brief civil protection authorities. These bodies keep planetary defense bigger than any single country, which matters because orbits, and consequences, don't respect borders. So why put all that attention on 3i Atlas if it's not a threat? 3 big reasons. First, it's unusual. Interstellar objects don't fit the standard templates, and unusual things are how you stress test a system. Second, every precision measurement strengthens the wider catalogue. The same techniques and communication channels used here are the ones we'd rely on for a real hazard. Third, It's prime science. Planetary defense and planetary science are intertwined. The better we understand what these objects are made of and how they behave, the better we can predict, model, and if ever necessary, deflect. That last word, deflect, used to be theory. In 2022, NASA's DART mission slammed a spacecraft into the small moonlet Dimorphos and measurably changed its orbit, demonstrating kinetic impact as a viable deflection method. Follow-up papers showed the momentum transfer was amplified by the spray of ejected material, an encouraging sign for future options. Europe's Hera mission, launched in 2024, is on its way to survey the aftermath in detail and lock down the physics that models still debate. In other words, we're not just watching the sky, we're practicing what we'd do if watching ever wasn't enough. Looking ahead, the network keeps upgrading itself. A dedicated infrared space telescope called NEO Surveyor is in development to hunt the hard-to-see dark asteroids that reflect little sunlight. By sensing their heat, it will find many of the larger, potentially hazardous objects more quickly and with better orbits from the start. That's prevention in its purest form. Discover earlier, refine faster, rest easier. All of this brings us back to the present moment. When you hear that the Planetary Defense Network is activated to monitor 3i Atlas, picture a lot of quiet, disciplined work. Survey telescopes adding dots to a growing track. The MPC posting those dots so the world can aim more telescopes. CNEOS running risk checks and sharing the results openly. Radar time penciled in if geometry cooperates. And Aya Owen ensuring that scientists and the public are reading from the same script. No sirens, no panic. Just a well-rehearsed team doing what it was built to do, turn a mysterious, fast-moving speck into a well-understood visitor, and use the experience to make the system better for the next one. Picture a quiet winter night in the Andes foothills of northern Chile. The Atlas telescope at Rio Hurtado is doing what it always does, snapping short exposures of huge swaths of sky, then comparing tonight's frames with last night's to see what has moved. Near dawn on July 1st, 2025, UT, the software flags a faint speck that slides between frames in just the right way to make astronomers sit up. Within hours, the detection from this NASA-funded University of Hawaii-operated survey is routed to the Minor Planet Center for the world to see. That little moving dot will soon be known as 3i Atlas, only the third confirmed interstellar visitor in history. Atlas is built for moments like this. Each unit is a wide-field, half-meter telescope designed to scan the entire visible sky several times per night, hunting for anything that shifts against the background stars. Its power isn't just in optics, it's in the cadence and the coverage. With identical systems in Hawaii, South Africa and Chile, Atlas stitches together a near-continuous skywatch, so a fast, faint object has fewer chances to slip by unnoticed. The Chile site, coded W68, fills a crucial southern gap and can work lower along the crowded Milky Way star fields than the northern scopes can reach. The first entry for the new object appears on the Minor Planet Center's confirmation page under an internal tag, 11PL3Z, just enough to mobilize follow-up observers across the globe. That page is astronomy's switchboard. Once a candidate is posted, professional facilities and skilled amateurs alike pounce, measuring positions to refine the path. In this case, the MPC issues a formal bulletin the next day, MPEC 2025 and 12, announcing that the newcomer is not just unusual, but interstellar, and assigning names that will stick: 3i Atlas for its interstellar status, and C/2025 and 1 Atlas for its cometary nature. Those first 24 to 48 hours are a blur of telescopes handing the baton from west to east and back again. As the measurements stack up, the what is it question sharpens. Early images look point-like, as if it might be an asteroid, but deeper exposures from larger observatories reveal a faint fuzzy halo, the telltale coma of a comet waking up in sunlight. That subtle softening is the moment 3i Atlas stops being merely a moving dot and becomes a physical story, an icy body actively venting gas and dust as it enters warmer space. Meanwhile, astronomers perform one of Discovery's most powerful tricks. They look backward in time. Teams comb through recent and archival images from other surveys to find pre-coveries, earlier, unnoticed snapshots of the same object. The Zwicky Transient Facility, ZTF, at Palomar digs up observations from June and even deeper stretches of the inbound path. These pre-discovery detections lengthen the track on the sky, which tightens the derived path through space and cements the interstellar verdict. 3i Atlas wasn't born here. It's cutting through on a one-time, never-to-return trajectory. NASA's public note lands almost in sync with the MPC announcement, an animation showing the original Atlas frames and a plain-spoken summary, discovered July 1st by the Atlas Chile telescope, on an open, incoming path from beyond our solar system, exciting, unusual, and safely distant. That quick, clear messaging becomes part of the Discovery story too. It signals to the community and the public that this is a rare scientific opportunity, not a cause for alarm. Inside the Atlas pipeline, the flow is routine but relentless. A 30-second exposure, a 10-second readout and repoint, and repeat thousands of times per night feed the detection software that measures positions against catalogues, rejects false matches, and boosts promising movers. That cadence is why the system can catch something as faint as 3i Atlas while it's still far from the Sun and Earth. The Southern Station's location at L-Source Observatory, West 68, is especially valuable for sweeping along the galactic plane, where a dense backdrop of stars makes moving specks easy to miss. In a sense, the Chile telescope was the right tool in the right place at the right time. As the orbit solution firms up, follow-up moves beyond where is it to what is it made of. Spectrographs start splitting the comet's light, and big telescopes sharpen the view of its coma and tail. But those first 2 days remain the heartbeat of the tale. Atlas posts, the MPC coordinates, the worldwide network answers, and 3i Atlas graduates from anonymous code to named interstellar comet. Fast. That choreography didn't happen by accident. It's the product of years of investment in surveys, data standards, and open reporting so that when a once-in-years object appears, everyone knows their part. From a storyteller's perspective, the charm of the discovery is how ordinary steps produced an extraordinary result. No single eureka image, no cinematic zoom in, just a patient sky patrol catching a faint traveller in routine frames. Then the community's collective reflex turning a handful of pixels into a confident narrative. A comet from another star system is in our sky. The dates and instruments will go in the record books, but the deeper lesson is about vigilance. 3i Atlas was found because surveys like Atlas keep looking, night after night, exactly so that rare things don't slip past. By the time the first weekend after discovery rolled around, pre-coveries had extended the object's timeline. The comet versus asteroid question was leaning decisively toward comet, and the first public explainers were already emphasizing 2 key points. This is interstellar and it's safe. With perihelion slated for late October 2025 and a wide berth from Earth, the rest of the story would be about science, what this messenger from elsewhere carries in its ices and dust, and about how a global network turned a tiny moving smudge into a milestone. Think of the solar system as a great slow-moving roundabout. Planets and most comets loop around in lanes that eventually bring them back. The path of 3i Atlas isn't a loop at all. It's a one-time sweep across the roundabout that never closes. We can trace that arc using a handful of anchor dates. It was first reported on July 1st, 2025 by the Atlas telescope in Chile and formally logged as C/2025 N1 Atlas. From the start, its motion told astronomers this was a visitor from beyond our system, not a long-period comet making another return. As summer turned to autumn, 3i Atlas slid inward on a steep retrograde path that just skims the plane of the planets. The The first big rendezvous on the calendar was with Mars. Around October 3rd, 2025, it passed the red planet at roughly 0.19 astronomical units, about 30 million kilometres. That made Mars the only world to get a relatively close look during the inbound leg, and space agencies lined up their orbiters to try for observations. From Earth, however, the geometry was lousy. Through October, the comet crept closer to the Sun in our sky, making it increasingly difficult to spot from the ground. Right after the Mars flyby came solar conjunction, when the comet slipped behind the Sun from Earth's point of view. That happened in the third week of October, which is why even large observatories had to pause. The very moment everyone wanted most, the turn around the Sun was happening out of view. This conjunction window straddled the headline milestone, perihelion, the comet's closest approach to the Sun, landing around October 29th to 30th, 2025, at roughly 1.36 to 1.4 astronomical units, just inside Mars' orbit. The object was moving fastest at this point, curving around our star before setting course for the outer darkness again. Once 3I Atlas cleared the Sun's glare in early to mid-November, it returned to pre-dawn skies as a faint telescopic target. The outbound leg stacked up more waypoints. A pass near Venus on November 3rd, 2025, still comfortably far at about 2/3 of an AU, and then the date most people ask about, closest approach to Earth, on December 19th, 2025. Even then it keeps a huge margin, about 1.8 astronomical units, nearly twice the Earth-Sun distance, meaning no hazard and no naked eye show. By late December, it drifts through Virgo toward Leo while fading, its tail geometry changing as the angle to the Sun opens up. After New Year's, the story shifts to the giant of the outer solar system. On March 16th, 2026, 3I Atlas passes about 0.36 astronomical units from Jupiter, still far but close enough that professional teams will watch for any subtle changes that encounter might imprint on the dust tail. Then it's goodbye. With a path that isn't bound to the Sun, the comet will fade below reach of most telescopes and head back into interstellar space, carrying whatever traces of our neighbourhood it picked up, a thin frosting of solar-heated dust into the dark. A few practical takeaways make the whole flight plan easy to remember. First, nothing about this trajectory brings it near Earth. The minimum distance is on the order of 270 million kilometres, and that happens well after perihelion, when it's already on the way out. Second, the best observing opportunities cluster after it emerges from behind the Sun, in mid-November mornings, and then again through December, as it climbs higher before fading. Third, if you're following along with spacecraft, the Mars date in early October 2025 and the Jupiter date in March 2026 are the two moments when robotic eyes have the best chance to catch it from up close, by space standards. All of that sits on top of the firmest anchors we have, NASA's perihelion timing and distances, the Minor Planet Center's designation, and the community's live tracking. So the timeline you've just heard is the bones of the story. In, around, out, and gone. Start with the simplest truth. We don't actually see the solid heart of 3I Atlas yet. We see sunlight bouncing off the dust and gas it sheds. That glowing envelope, the coma, hides the nucleus and makes size tricky. Hubble's first close look put a strong ceiling on the size. The nucleus can't be bigger than about 3.5 miles, 5.6 kilometres, across, and it could be as small as roughly 1,000 feet, 320 metres. In other words, imagine anything from a big city block to a small mountain hidden inside that haze. Those same Hubble images also show a teardrop-shaped dust plume, lifting off the sunlit side, a classic comet waking up signature. Why such a wide range? Because brightness is a blend of nucleus plus dust. If the dust is abundant or made of very reflective grains, it can fool you into thinking the core is bigger than it is. That's why mission teams use repeated images to model the coma, subtract its contribution, and then bracket the nucleus. Hubble's constraint, 320 metres to 5.6 kilometres, is our best so far and already suggests 3I Atlas could be larger than 2 I/Borisov's nucleus, which Hubble capped at under about 1 kilometre. But until the haze thins, or a spacecraft flies by, we'll talk in ranges, not single numbers. Speed is the easy headline, 3I Atlas is absolutely flying. Hubble's team calls it the fastest solar system visitor on record, about 130,000 miles per hour, roughly 209,000 kilometers per hour, as it knifes through the inner system. That speed will peak around its closest pass to the Sun at the end of October, then ease a bit as it heads back into deep space. This isn't a loop, it's a one-time open-ended pass, so nothing slows it into a return trip. Fast in, faster at the turn, then gone. Now the fun part, what it's made of. First results from the James Webb Space Telescope paint a striking picture. Webb's infrared spectra reveal a coma unusually rich in carbon dioxide compared to water, about 8 times more CO2 than H2O by molecule count at the time of observation. That ratio is among the highest ever measured in a comet. Alongside CO2 and H2O, Webb sees carbon monoxide, traces of other sulfur-bearing molecules, solid water ice grains and dust. In plain English, 3I Atlas is venting a cocktail we do see in comets, but the proportions are weird, in a scientifically exciting way. What could that mean? 2 leading ideas are on the table. 1, the comet formed closer to its original system's carbon dioxide snowline, where CO2 would freeze out more readily than water, baking in a CO2-rich recipe from birth. 2, its outer layers were altered by intense radiation over eons in interstellar space, so CO2 escapes more easily than water when the Sun starts heating it. Either path tells us 3I Atlas carries a chemical accent from a kitchen very different from ours. Meanwhile, another telescope adds an important counterpoint. NASA's Swift Observatory detected the telltale glow of hydroxyl, a product of water breaking apart in sunlight, confirming that water is definitely present and already escaping even when the comet was still far from the Sun. That early water-on behaviour, at distances where water usually stays quiet, suggests some of the water might be hitchhiking on lofted icy grains, not just boiling straight off the surface. It's a subtle clue about how the nucleus warms and crumbles grain by grain. Ground-based giants are filling in the picture from another angle. Gemini and other observatories have imaged the tail growing and changing shape as activity ramps up, while Hubble's dust plume snapshot helps estimate how much material is leaving the nucleus per second. Put together, these data say 3I Atlas is behaving like a normal comet in its mechanics. Sun heats ices, ices sublimate, dust is carried away, while being abnormal in its mix, especially the carbon dioxide dominance. That combination, ordinary physics, unusual recipe, is exactly what makes it a goldmine for comet science. A few working truths you can say with confidence. The nucleus is still unresolved and could land anywhere within that Hubble range. The object is tearing through the inner solar system at roughly 130,000 miles per hour. It reaches its closest to the Sun point around late October at about 1.4 times Earth's distance from the Sun, and it never comes remotely close to Earth, minimum distance about 1.8 times the Earth-Sun gap. Those anchor points set the stage for everything we learn next. As more spectra arrive, scientists will watch whether the CO2 over water story stays extreme or evolves. If water begins to dominate later, that may mean the early outgassing was from a crusty, CO2-rich skin that blew off to reveal wetter layers beneath. If CO2 stays king, that strengthens the case for a truly CO2-rich body from an alien nursery. Either outcome is valuable. It tells us whether 3I Atlas is a quirky outlier or a preview of a whole population our surveys are only now able to catch. And that's the beauty of this moment. Size, speed, and makeup aren't just trivia. They're the keys to a bigger story about how worlds form around other stars. A small nucleus with a huge CO2 budget hints at cold carbon-rich building blocks. A larger nucleus with stubbornly CO2 heavy outgassing could point to crusts and layers we rarely see in local comets. Whatever the final mix, 3I Atlas is handing us laboratory-grade data from another solar system. No equations required, just careful listening to what its light is telling us. When a cold, dusty iceberg like 3I Atlas drifts inward, sunlight is both alarm clock and sculptor. The first thing you see is not the solid heart but the atmosphere it builds around itself. A pale, gossamer coma that swells as buried ices warm and turn to gas. That gas escapes through weak spots and vents, dragging dust into space and carving narrow jets that look like pressure hoses switched on in the dark. Even a single steady jet can make the coma lopsided, brighter on the sun-facing side feathered into a subtle fan. Hubble's early portrait caught exactly that, a teardrop-shaped cocoon and a distinct dust plume lifting off the sunlit face, with the first hint of a tail peeling away. It was the wake-up photo, proof that this interstellar traveller behaves, at least in its mechanics, like a normal comet stirred from sleep. From there the show gets richer. Comets carry two very different kinds of tails, born from two different forces. The dust tail is made of tiny grains pushed gently by sunlight. It tends to curve like smoke caught in a breeze. The gas, or ion tail, is made of molecules blown straight back by the solar wind. It's taut, narrow, and points almost directly away from the sun. Which one you see best depends on how active the comet is, how you're viewing it, and what the sun is doing that week. Already, big ground telescopes have watched 3I Atlas's dust tail grow through late August and early September, the coma expanding as activity ramps up. Textbook behaviour as it nears the sun. Composition is the wild card, and this is where 3I Atlas gets weird in a scientifically delicious way. The James Webb Space Telescope sniffed the coma and found an unusually carbon dioxide-rich mix, far more CO2 relative to water than is typical for comets at similar distances. That skewed recipe matters for the look of the comet. CO2 can switch on strong jets earlier and farther from the sun than water usually does, so you can get vigorous sunward-facing plumes while the comet is still relatively far out. Think of CO2 as a more eager kettle on the stove. It boils sooner, it vents harder. That helps explain why images show a dominant sun-facing plume so early in the apparition, and why the tail has been evolving quickly as heating intensifies. By late August, Gemini South's cameras were catching that evolution in real time, the tail lengthening, the coma fattening, the overall shape becoming more obviously comet-like with each pass. A month of snapshots is enough to see day-to-day personality, little kinks and kites in the tail as dust grains of different sizes peel off and feel sunlight differently. Because dust is lazy compared to gas, it remembers where it came from. The tail is, in a sense, a logbook written in powder, with each streamer marking a past outburst or a favoured vent. Then there are the dramatic moments when a jet points right at the sun. Fresh images taken just before solar conjunction showed 3I Atlas throwing a conspicuous sunward jet, an arrow of dust and gas punching up the bright side of the coma. That can look counterintuitive. Shouldn't the tail point away from the sun? But jet direction is about where the active vent is on a rotating nucleus, not about the tail itself. The tail still forms anti-solar. The sunward jet is a fountain on the front lawn. As the nucleus spins, that fountain sweeps like a lighthouse beam, imprinting gentle arcs and striations into the coma that time-lapse photographers can catch over hours. Watch closely and you'll see how geometry plays tricks. When we stare almost down the comet's orbital plane, a ribbon of dust can masquerade as a spike that seems to lean sunward, an effect observers casually call an anti-tail or sunward spike. Shift the viewing angle by a few weeks, and that spike relaxes into the more familiar anti-solar tail. None of this needs exotic physics. It's choreography. The comet's rotation, our line of sight, and the steady shove of sunlight acting together to redraw the same material into different shapes as days pass. This is common in active comets and is exactly the kind of day-to-day evolution imagers have been documenting around 3I Atlas. All the while, the solar wind is writing its own signature into the gas tail. If 3I Atlas's ion tail brightens enough to be seen routinely, expect it to be straighter and more temperamental than the dust tail, prone to kinks, twists, and if a solar storm hits, sudden disconnection events, where a segment snaps off and drifts away like a torn streamer. Even when we don't see the ion tail clearly in pictures, spacecraft can feel it. Instruments far from Earth may catch the gust of charged particles, or pick up the spectral fingerprints of certain gases as the comet sweeps by their field of view. With multiple missions lining up observations this season, we could get a rare multi-angle look at how the comet's outflow mingles with the sun's breath. Under the hood, it's the nucleus's spin and surface patchwork that set the rhythm. A slowly rotating comet may show long, steady fans from the same regions every night. A faster spinner can paint pinwheel patterns, faint corkscrews etched into the coma as the jet sweeps around. Crusty areas can bottle up gas until pressure fractures the surface and boom! An outburst briefly boosts the tail. Because 3I Atlas is interstellar, its crust could be tougher or more sun-shy than we're used to, with CO2-fed jets dominating early and water-fed activity joining later as deeper layers warm. That staged awakening would naturally change the colour, brightness, and grain sizes in the tail over the next few months. Webb's initial chemistry result is our clue. The rest of the season will test whether the mix evolves in step with the heating. For observers, the practical takeaway is simple. This comet is dynamic on human timescales. A night-to-night comparison can reveal new streamers or a shifted sunward fan. A week can add tens of thousands of kilometres to the dust tail. A solar hiccup can ripple the gas. When 3I Atlas re-emerges from the sun's glare, long exposure images should again pull out the faint tail, while high-contrast processing around the nucleus may show delicate jets curling off the bright crescent of the coma. It won't be a naked-eye spectacle, but it will be a masterclass in how sunlight sculpts fragile worlds. And that's the deeper story of the weirdness. 3I Atlas isn't breaking the rules of comets, it's playing them with an unfamiliar instrument. The physics, ice swarms, gas vents, dust flies, sunlight and the solar wind push are comfortingly old. What's new is the score, a carbon dioxide forward chemistry that turns on jets early, a rare interstellar provenance, and a flight path that gives us only a short window to watch the art happen. By reading its jets like handwriting and its tail like a weather vane, we're learning not just what this traveller is, but how comets from other suns might look and behave when they wander into our light. When people say the network is on alert, picture a huge, well-rehearsed pit crew, survey telescopes that never sleep, follow-up observatories that dissect light into chemistry, radar dishes that can measure distance to a target with mind-bending precision, and data hubs that keep everyone in sync. That whole orchestra is tuned to a rare key right now because of 3I Atlas. Not for drama, for detail. The goal is to wring every scrap of information from a once-in-years visitor and turn it into hard facts the whole world can use. The first eyes are the all-sky surveyors. Atlas, the NASA-funded Asteroid Terrestrial Impact Last Alert System, runs 4 wide-field telescopes, Hawaii ×2, Chile, South Africa, that sweep the sky several times each night and flag anything that moves. Its Chile station at Rio Hurtado picked up the now famous moving speck on July 1st, 2025, kicking off the story of 3I Atlas. Alongside Atlas, Pan-STARRS in Hawaii, the Catalina Sky Survey in Arizona, and the Zwicky Transient Facility, ZTF, at Palomar are all workhorses of planetary defense. In fact, ZTF dug up pre-discovery images of 3I Atlas months before discovery, extending its track deep into the past. This surveys plus pre-coveries tag team is how a faint stranger becomes a precisely tracked visitor. The moment a survey flags a candidate, the Minor Planet Center, MPC, switches on the global switchboard. observers everywhere rushed to add positions. Within a day of discovery, the MPC issued MPEC 2025-N12, giving the object its interstellar 3I designation, and the cometary name C/2025-N1, Atlas. That single bulletin turned scattered measurements into a community target, with shared ephemerides, consistent formatting, and a place for new data to land. From there, JPL's Center for Near-Earth Object Studies, CNEOS, does what it always does: continuous orbit solutions and risk checks. Its automated Sentry system scans the catalogue for any possible future impacts, not an issue here. Its rapid response scout tool checks brand new finds. Most days that means nothing to worry about, and that too is the point. 3I Atlas is a scientific opportunity, not a hazard, and PDCO's pipeline is built to say so clearly and fast. Then the big guns of follow-up come online. The Hubble Space Telescope pinned down the coma's shape and set the tightest size bounds so far on the hidden nucleus, no larger than approximately 5.6 kilometers across, and possibly as small as approximately 320 meters, while also catching a bright dust plume off the sunward side. The James Webb Space Telescope went further, splitting the infrared light and finding that the coma is unusually rich in carbon dioxide compared to water, among the highest CO2/H2O ratios ever measured in a comet, implying either an alien nursery with different freezer lines or surface layers altered by long interstellar exposure. SWIFT, NASA's ultraviolet observatory, added the clincher for water by detecting hydroxyl, a UV byproduct, even when the comet was still far from the Sun. Together, these three space telescopes are the chemistry team, each probing wavelengths the others can't. On the ground, the giant mirrors are busy too. Gemini South, NSF's Neuer lab, has been imaging the growing tail and swelling coma, giving us a time-lapse of how activity ramps up as sunlight digs in. At ESO's Very Large Telescope in Chile, spectrographs like X-Shooter, UVEs and MUSE have been taking deep, wideband spectra to pick out faint gases, China, NEI and more, and map how jets paint structure into the coma. Keck in Hawaii has joined the chase as well, adding high-resolution looks and reports of an anti-tail geometry caused by viewing angle and dust dynamics. This is the fine detail crew. They reveal what the comet is doing from night to night, molecule by molecule, streamer by streamer. Close to the action, the fleet at Mars just proved why having cameras all over the solar system matters. As 3I Atlas swept past Mars in early October, ESA's ExoMars Trace Gas Orbiter snapped the closest views yet, a tiny, fuzzy bead, but precious, for geometry and brightness, and agencies coordinated to try for additional looks. NASA's own public brief before the flyby made it clear, multiple spacecraft at Mars might catch a glimpse. Even when the images are modest, they nail down the comet's position and behaviour from a second vantage point, gold for orbit refinements and activity models. Looking ahead to the outbound leg, there's been lively discussion about whether Jupiter region assets could contribute as 3I Atlas passes the giant planet in March 2026. Proposals and think pieces have floated ideas for Juno or other missions to observe, but as of now these are concepts and community conversations, not approved retargetings. Still, even remote sensing, UV/IR/radio, from existing instruments could sample the ion tail or dust environment if geometry cooperates. That's the nature of opportunistic science. Plan if you can, be ready if you can't. Not every tool fits every target. Planetary radar, for example, is one of Planetary Defense's sharpest rulers. Goldstone can shrink orbital uncertainties in minutes for suitable near-Earth objects, but 3I Atlas will never come close enough, or be radar bright enough, for practical imaging. Radar remains central for hazardous asteroids. For a distant, fluffy interstellar comet, the job falls to optics and infrared. Knowing which instrument not to use is part of the craft. Behind the scenes, the coordination layer hums. the International Asteroid Warning Network has spun up a dedicated 3i Atlas comet astrometry campaign, complete with a techniques workshop, to help observers extract cleaner, less biased position measurements from a fuzzy target. That may sound nerdy, but precise astrometry is what keeps the ephemerides tight and the science sharp, especially for a comet whose jets can tug the measured centre off the true nucleus. It's also a fire drill that improves the whole ecosystem for the next unusual object. Tie it all together and you get a layered defense science stack doing exactly what it was built to do. Surveys like Atlas, Pan-STARRS, Catalina and ZTF keep the sky under surveillance. The MPC and CNEOS keep the math honest and the messaging clear. Space telescopes, Hubble, Webb, Swift, TESS, and big ground facilities, Gemini, VLT, Keck, tease out physics and chemistry, and international groups like IAW keep everyone rowing in rhythm. The result isn't sirens, it's signal. A shared, evolving portrait of 3i Atlas that will outlast the comet's brief passage and make us better at catching, classifying and understanding the next visitor from between the stars. Open the envelope and read what the light says. That's the heart of the science payoff with 3i Atlas. It's a letter from another planetary nursery, written in gases, dust and sunlight. When telescopes break that light into its ingredients, we aren't just learning about one comet. We're peeking at how some other star system mixed its ices, built its worlds, and stored its carbon, oxygen and water during planet formation. The first headline from those ingredients lists is striking. The gas around 3i Atlas is unusually rich in carbon dioxide compared with water. The James Webb Space Telescope measured a CO 2 to H2O ratio that ranks among the highest ever seen in any comet, a genuine outlier when you stack it against our local family. That one number matters because it encodes where and how the comet likely formed, closer to a region of its original disk where CO2 could freeze easily, or with outer layers altered by long exposure to interstellar space, so that CO2 vents earlier and more forcefully than water when warmed. Either way, the chemistry is a loud hint that not every planetary system cooks its comets the way ours does. Water is very much part of the story too. Ultraviolet observations picked up the telltale signature of water breaking apart in sunlight, showing that 3i Atlas was already shedding H2O even while it was still far from the sun. That's key context. If CO2 starts the show early, water joins in as heating deepens, and the changing balance over time lets scientists map layers in the nucleus, crusts that vent different ices at different distances. Watching that handoff unfold in real time is like slicing a core sample from a glacier and reading its seasons, except the seasons here happened under an alien sun. High-resolution images add another layer of clues. Hubble's early portraits pin down a tight upper limit on the hidden nucleus, no larger than a few miles across and possibly as small as a few 100 meters, and caught a sunward dust plume, proof of active jets and a coma shaped by daylight. Size bounds matter for physics. Combine them with the measured brightness and gas/dust release, and you can estimate how fast material is leaving, how reflective the dust is, and how porous that buried ice might be. Each of those quantities feeds straight into models of how comets crust over, crack, and respond to warming, models we then test against comets born around other stars. Put those pieces together and you start answering big questions. How common are CO2-heavy comets in the galaxy? Are we seeing the same diversity we've already glimpsed in our own backyard, where some comets are unusually rich in carbon monoxide or nitrogen, compounds? Or are interstellar visitors sampling corners of planet formation we rarely touch? The previous interstellar comet 2I/Borisov surprised astronomers by being rich in carbon monoxide relative to water, already a sign that other systems can stockpile volatiles differently. 3i Atlas pushes that theme further with its CO2 forward mix, suggesting that the family recipe for comets beyond the Sun is truly varied. That diversity, measured object by object, is how we'll calibrate the chemistry of young planetary systems we can't visit. There's a habitability angle too. In many formation theories, comets shuttle ices and organics across a newborn system, seeding young worlds with water and carbon-bearing molecules. If 3I Atlas is representative of a CO2-rich population, that implies some planetary systems may deliver different volatile packages to their rocky planets than ours did. More CO2 early on could change the climate trajectories of infant worlds. Less water changes the odds for oceans. We're not leaping to conclusions from one object, but each interstellar visitor tightens the constraints on these delivery budgets, shrinking the space of what's plausible for exoplanet climates and surface conditions. Another payoff is pure mechanics: jets, tails, and time. As 3I Atlas warms, its jets act like tiny thrusters, and the dust records their rhythm in the shape of the tail. By tracking how the tail curves and how the coma brightens night to night, scientists infer the spin of the nucleus, how many active regions it has, and whether those vents flicker or roar. Because this traveller doesn't belong to our sun, the patterns we measure aren't just a repeat of what we see in long-period comets from our own Oort cloud. They're a fresh data point from different starting conditions. That helps us tell apart what's universal comet physics from what's just home team habit. Comparisons across all three interstellar visitors sharpen the picture. Oumuamua offered a puzzle with no visible coma. 2I/Borisov behaved like a classic but CO-rich comet. 3I Atlas looks like a vigorous carbon dioxide forward comet with early water activity. Line those up and you get a spectrum, from dry or crusted to CO tilted to CO2 tilted, that hints at different birthplaces inside protoplanetary disks and different surface histories in deep space. With each new point on that spectrum, our theories about where these bodies form, relative to the various snow lines where ices can condense, get tested, refined, or broken. That's progress. The practical side of the payoff is just as important. 3I Atlas is a stress test for our observing playbook. Coordinated campaigns between space telescopes and big ground-based observatories are showing what works best, when, and why. Techniques honed here. How to extract precise positions from a fuzzy, jet-pushed coma. How to interleave Hubble imaging with web chemistry and quick turnaround UV detections. How to communicate cleanly to the public. Become the standard operating procedure for the flood of interstellar objects future surveys are expected to find. The result is a sharper, faster, more reliable pipeline from faint spec to physical understanding. And finally, there's the simple, audacious promise of data that outlives the moment. The spectra, images and light curves we're collecting now will be mined for years, reanalyzed with better models, compared against new visitors, and folded into exoplanet and disk chemistry studies that barely exist yet. 3I Atlas will be gone, but the measurements won't. They'll sit in archives next to those from Oumuamua and 2I Borisov, forming the first small library of extrasolar cometology we've ever had. Page by page, that library tells us where these objects were born, what they carried with them, and how diverse planet-making really is across the galaxy. That's the message in the ice, and it's worth reading slowly. Start with expectations. 3I Atlas is not a look-up-and-wow comet. It's a faint telescopic target, far too dim for naked-eye viewing, and generally out of reach for binoculars, unless you're stacking long-guided exposures with a camera. If you've got a small to mid-sized telescope and dark skies, you're in the game. If you're hoping to see it by eye from the backyard, you'll be disappointed. That's not a failure of the comet. It's just honest physics and distance. The calendar explains a lot about why it's tricky. Before its closest swing by the Sun, 3I Atlas ducked into solar conjunction, too close to the Sun in our sky to observe, then turns the corner at perihelion around the end of October. The good news is it reappears afterward in the pre-dawn, giving observers a real shot through mid-November into December before it fades. Think morning comet. The hour or so before sunrise is your window. Where should you look? As it emerges from the sun's glare, you'll find it low in the east before dawn, and climbing a bit higher each week. Star charts and live sky maps place it against Virgo in late October/early November, then drifting toward Leo through December. The exact line on the sky shifts with your latitude and the date, so don't wing it. Use a Planetary map or an online ephemeris and search for C/2025 N1 open (Atlas close parenthesis). How bright is faint? Predictions hover around the low teens on the astronomical magnitude scale, about the realm where an 8-inch, 200mm telescope under dark, transparent skies can show a soft, round glow with a brighter centre and maybe the whisper of a tail in long exposure images. In suburban light pollution, you'll want more aperture, better transparency, or a camera to help. Don't be surprised if it looks like a small hazy patch rather than a sharp point. You're seeing the coma, not a star. And remember, comets are notoriously unpredictable. Outbursts can happen, and the brightness curve can drift. But you should plan as if it will stay challenging. A few observing tips make a big difference. First, pick your time. Aim for a start about 90 minutes before local sunrise, when the object is highest and the sky is still dark. Second, maximize contrast. Dark sight, good transparency, and fully dark adapted eyes. Third, use the right eyepiece. A wide field, low power view, say 30 to 80 times, gathers more of the diffuse glow. If the core pops, nudge the power up a bit to tease out a brighter centre. Fourth, nudge the scope gently. Subtle motion across the field helps your eyes separate the comet's soft haze from the background. Finally, sketch or snap a quick image. Even a short, tracked exposure can reveal a tail your eye might miss. If you're imaging, think many short subs rather than a few long ones. Track the sky with a mount, shoot 15 to 60 second exposures at moderate focal length, and stack on the comet if your software allows. That keeps the comet sharp, even as stars trail a little. A neutral processing touch is best. Lift the faint outer coma and tail without blowing out the core. Over several nights you may see the tail geometry change as your viewing angle and the comet's activity evolve. Tiny, gratifying proof that you're watching a living object. Because this is an interstellar visitor, people worry about safety. The observing plan itself reassures you. Even at its closest to Earth in December, 3I Atlas remains very far away, roughly on the order of 270 million kilometres, so there's no hazard, and correspondingly, no bright show. That huge distance is why telescopes and cameras, not eyeballs, are the tools of choice here. For practical wayfinding, lean on tools. A reputable live sky map or a planetary map with up-to-date orbital elements will get you within the same eyepiece field on the first try. Many even show a finder circle that matches your telescope's true field of view. Cross-check with an online comet tracker before you head out so you're not fighting yesterday's position. If you'd like old-school star hopping, anchor from bright guide stars. Spica in Virgo early on, then toward the sickle of Leo later in the year, using printed charts with a comet plotted for your date. From a when should I try standpoint, here's the simple playbook. Skip late October while it's too near the sun. Begin attempts after it clears conjunction and rises into the morning sky in November. Make your main push in late November through the first half of December when it's highest before dawn. And expect it to fade through the holidays as it coasts outward. If you only have one shot, pick a moonless morning during that late November, early December window. Even then, set expectations. You're hunting a dim, diffuse glow, not a sword of light. One last thing to keep in mind is that hard to see doesn't mean not worth seeing. The thrill here is subtle. You're catching photons from a traveller that began life around another star. Through the eyepiece, it may look like a small, smoky seed. On a stacked image, it becomes a soft lantern with a faint tail, changing shape week to week as sunlight sculpts it. That's a humble view, but it's also a profound one. Lots of comets put on a better show. Almost none have come from so far away. Think of the rest of this year as a timed window you can plan around. The immediate milestone is the turn around the Sun. 3i Atlas reaches its nearest point to our star around October 29th to 30th, 2025, at roughly 1.4 times the Earth-Sun distance, comfortably inside Mars' orbit, but still far from the inner planets. It's also tucked in the Sun's glare for us right then, so the moment of maximum heating and activity happens offstage from Earth. That's normal. Conjunction hides a lot of the good stuff. The payoff begins right after. As November opens, 3i Atlas slides back into pre-dawn view, low in the east before sunrise. Expect a faint telescopic glow with a compact core and a wider, softer haze, a coma that's been pumped up by the perihelion heat. Activity often stays strong for weeks after the turn, so imagers will be chasing fresh jets, changing tail structure, and maybe the occasional hiccup as crusty patches crack. This is the phase where nightly changes can show up in long stacked images, even if the comet never becomes an eyeball spectacle. The key date most people ask about, closest to Earth, arrives well after that. December 19th, 2025. Even then, our visitor keeps a very healthy buffer, about 1.8 astronomical units, roughly 270 million kilometers. That's why there's no danger, and also why there's no naked eye show. If you're observing, the sweet spot is those moonless, crisp mornings from mid-November into early December, when the geometry improves day by day before the comet begins its slow fade. Behind the scenes, spacecraft and big observatories will keep stacking data. The Mars encounter on October 3rd already gave orbiters at the red planet a front row seat. Next up are opportunistic alignments in early November, when the comet's long, straight ion tail may drape across the paths of far-flung spacecraft. One prediction places NASA's Europa Clipper in the right place between October 30th and November 6th to taste a sprinkling of ions that originated from the comet, harmless to the craft but potentially a tiny direct sample of interstellar material snagged by the solar wind. Whether the instruments can be switched on in time is a separate practical question, but the alignment is a rare chance. Closer to home, ground and space telescopes will be watching for how the recipe evolves after perihelion. Early spectra flagged an unusually carbon dioxide-rich mix compared to water. Now scientists want to see if that balance shifts as deeper layers warm. If water output ramps and CO2 calms, it hints at a skin that's different from the interior. If CO2 stays dominant, it strengthens the idea that this body was born in a part of its original star's disk where CO2 froze out easily. Either way, the next 6 to 10 weeks are prime time for chemistry, and that story will be told in infrared and ultraviolet as much as in pretty pictures. December is a tale of distance and discipline. 3i Atlas will be highest before dawn, and drifting through star fields that make for attractive wide-field frames, but its overall brightness should plateau in the faint telescopic range. Expect incremental changes rather than fireworks, the dust tail bending with our line of sight, the coma slowly shrinking as the fuel tank eases off, and the ion tail, if it's visible, occasionally showing kinks or disconnects when the sun's magnetic weather tugs at it. Think patient time-lapse more than single-night drama. After the holidays, the comet becomes a story for bigger mirrors and longer exposures. On March 16th, 2026, it will pass about 0.36 astronomical units from Jupiter, still a respectful distance, but enough that professionals will check whether the giant planet's realm leaves any imprint on the tail or helps carve subtle changes in the dust flow. For most of us on the ground, though, the target will be fading into the outer darkness by late winter and spring, filing itself under specialist object, while the rest of the sky steals back the spotlight. Meanwhile, the paperwork of discovery becomes the fuel for future insights. The Minor Planet Center's circulars have locked in the designation and the essential path. The NASA science page has done the public service of pinning dates and safe distances in plain language. From here, the timeline is straightforward. a brief post-perihelion observing window for the community, a closest to Earth date that's scientifically important but visually modest, a distant handshake with Jupiter, and then the long goodbye as 3i Atlas dims beyond reach. The data will outlive the show, landing in archives where they'll be compared against Oumuamua and 2i/Borisov and whatever the sky gifts us next. If you're writing this into a narrative, you can frame it in 3 beats: the hidden crescendo at the sun, the short season of morning sky science, and the fade to black as it exits stage right. The beauty is in the restraint. We're not getting a sword-in-the-sky comet. We're getting a laboratory object, a messenger that lets us watch sunlight sculpt alien ice in real time and, if the alignments pan out, lets our spacecraft feel the ions it leaves behind. When 3i Atlas slips away for good, what remains is a sharper playbook for the next interstellar visitor, and a thicker file on how other solar systems seed their comets. That's what happens next. A quiet, careful harvest of facts under crisp morning skies before the traveller disappears back into the dark. And that's where we'll leave it. A messenger from somewhere else, slipping through our sunlight for one brief season. 3i Atlas won't blaze across the night or rewrite our skies, but it has already rewritten our story about what's possible to find, to measure, and to understand. We watched a calm planetary defense network do exactly what it was built to do: notice quietly, coordinate globally, and turn a faint, fast speck into facts we can trust. No sirens, just signal. If this visitor has taught us anything, it's that wonder and discipline belong together. The wonder is simple. An iceberg of alien ice is breathing in our star's warmth, letting us read its chemistry like a letter from another nursery. The discipline is everything you didn't hear in the headlines, the patient surveys, the shared data, the night-to-night measurements that turn a rumour into a record. 3i Atlas reminds us that the universe rarely shouts. Most of the time it whispers. We just learn to listen better. So as it arcs away, smaller each morning, farther each week, remember what remains. The images and spectra will sit in archives, the models will improve, and the next time an interstellar stranger appears, we'll be sharper, faster, more curious than we were today. That is the real payoff. Not a spectacle, but a skill set. Not a scare, but a study. If this journey sparked questions or ideas, drop them in the comments. I read them all. Tell me what you want explored next. The deep mechanics of comet tails, how planetary radar pins down orbits, or the quiet heroes of the surveys that keep watch while we sleep. If this kind of clear, hype-free space storytelling is your thing, tap like so the algorithm knows, and subscribe so you don't miss the next chapter. Until then, keep a little room for the quiet kind of awe, the kind that finds you in the pre-dawn under a cold sky, knowing that a traveller from another sun just shared a few secrets and kept going. 3i Atlas is heading back to the dark. We'll be here when the next letter from the stars arrives.